So, we know that we can have a white dwarf star supported by the electron degeneracy pressure. Can we have something analogous supported by neutron degeneracy pressure? Well, here is the equation for the radius of a white dwarf, which we worked out by balancing the quantum mechanical pressure against gravity. And the same calculation should apply to something supported by neutrons. But what's going to change? Well, that's all a constant, that term, and this is a constant, and that's a constant, so those are not going to change. This whole thing here is telling us how many electrons you get per atom, which will be pretty much the same as the number of neutrons per atom. So we can ignore that. All that really matters are these two terms over here, because they're going to change. This is the mass of the white dwarf. A neutron star will be more massive than a white dwarf, but not by a huge amount, maybe 2 solar masses rather than 1 solar mass, and it's only to the 1/3 power, so that's not going to make a big effect. The crucial thing is going to be the fact that you've got the mass of the electron here, and for neutron degeneracy pressure we're going to have to replace that with the mass of the neutron. So by and large we expect the radius of a degenerate object, something supported by degeneracy pressure, to be inversely proportional to the mass of whatever particle is doing the pressure. Now neutrons have a mass 1840 times that of an electron, so that's telling us the radius should be 1840 times less. So instead of a typical white dwarf radius, which is maybe 6,000 kilometers, you divide that by 1840, end up with about 3 kilometers. In fact, it's a little more complicated than this. This is a gross approximation. In fact, the radius comes out as about 10 kilometers. So we've got the right order of magnitude, but out by a small factor. But nonetheless, that is absolutely tiny. Perhaps an analogy will help drive home just how small this is. Here is a view of Mount Stromlo. If we assume that a normal star, like our own Sun, is the size of the entire mountain, then a white dwarf is the size of the dome of the 74-inch telescope over here. So if that dome is the size of a white dwarf, a neutron star on that scale is about the size of this pebble.
All right, Paul, so you've shown us that if neutron degeneracy is in action, we're going to end up with a tiny little star that is almost the mass of our Sun, or even more massive than our Sun. So how much energy are we going to get making something big, for example, a big star, something very small? That strikes me as a good way to make a supernova.
Yep, so in this case, presumably we're going to talk about gravitational potential energy.
Yep.
That it'll start shrinking down as it goes in, it'll go faster and faster and faster.
Yep.
Whoop. And it'll form something that's too small to be much smaller than a pixel.
Seen.
But right in the middle, you're going to get that dense ball, and presumably the rest of the stuff's going to fall down and then bounce out somehow.
Right, so let's go through and calculate how much energy we're going to get making a neutron star, and then let's think about what happens once that neutron star is made, because that neutron degeneracy is going to stop the expansion. Then all that stuff coming in is going to want to pile in and bounce off, and we can figure out if this all makes sense.
So, how much energy can we get out of the collapse of a star? Now, this is a rather complicated process. You've got a star, and it runs out of fuel in the middle, so stuff starts falling in. A neutron star falls in the middle, more stuff rains down on top of the neutron star. Too complicated to solve for this problem, but let's make an approximation. Let's assume that the star collapses, leaving a shell of uncollapsed stuff, and a neutron star in the middle. So we'll assume the neutron star collapses really quickly. Let's say 1 solar mass, leaving, let's say the whole star was about 10 solar masses to begin with, so it leaves 9 solar masses sitting out here, and that distance is about the size of our own Sun, so about 700,000 kilometers. Now this is a gross approximation, but it won't give us too much of a wrong answer. We can now calculate how much energy we liberate as the shell falls down on the center. In reality, of course, some of the gas will not be falling from here, but falling from closer in. But on the other hand, the neutron star itself had to liberate some energy when it formed. So this is probably not going to be too far wrong, maybe a factor of 3 or 4 wrong, but it should be within an order of magnitude of the correct figure. So we've got a shell weighing 9 solar masses, which is going to fall 700,000 kilometers to land on the surface of a neutron star of radius about 10 kilometers. How much energy is released in this process? Well, this is a straightforward gravitational potential energy problem. It's basically dropping something. We're dropping, like a ball, a certain distance. Gravitational potential energy is given by G, mass of whatever is in the middle, so it's the neutron star, mass of the shell over the distance between them. So in this case, the change in gravitational potential energy, so the delta U, the change in energy, is equal to this at the beginning, the difference between this at the beginning and this at the end. So it's going to be G, M, neutron star, M, shell, 1 over R of the neutron star, so 10 kilometers, minus the starting distance 1 over 700,000 kilometers. Now you can see this is going to be vastly smaller than that, so we can actually just neglect that. So what we find is the energy released, that's the change in potential energy, is going to be, roughly speaking, G, M of the neutron star, mass of the shell, all over the final radius, which is 10 kilometers. So if we plug numbers into this, that's 6.67 by 10 to the minus 11. That's G. Mass of the neutron star is going to be 1 solar mass. So that's 2 by 10 to the 30 kilograms. Times the mass of the shell, that's 9 solar masses, times 9 times 2 by 10 to the 30. All over 10 kilometers, so 10,000 meters. Which comes out as about 2 by 10 to the 47 joules. Now if you remember, the type 1a supernovae we were talking about last time were only about 10 to the 44 joules, so we're talking about an absolutely staggering amount of energy here, 1,000 times more than the already staggering energy of a type 1 supernova. A huge amount of energy.